Okay, so here's our next video on analyzing limits, and this is another trick that you can use called the squeeze theorem or the sandwich theorem. And the way that this one works is, um, let's say that g is the function you're trying to take the limit for. So this one right here is the important one, right? Um, so if you're trying to find that one, but it's a complicated equation or just a weird graph and you're not really sure what it does, maybe you can find a simpler function called h that's always bigger than g around the point where you want to take your limit. And you can find a function f that's always smaller than the one that you want. And they squeeze g into a specific spot right around a. Okay? Because if they do that and you can figure out what h and f both do, then you can figure out what g does right in that spot. So, and that's why it's called the squeeze theorem. It squeezes g into a specific location, and in this case, it's L, right? Um, so let's use that theorem to do this example down here. Um, so the problem with plugging in 0 here is sine of 1 over 0 would be sine of infinity, essentially, or negative infinity. And that doesn't really, we can't figure out what that is because it varies between 1 and negative 1. So what we do know is this. We know sine of 1 over x is between 1 and negative 1. So that means that the function that we want, which is x squared sine of 1 over x, has to vary between whatever x squared is and whatever negative x squared is. Right? That's what we want. Well, let's look at what these two functions do when x is close to 0. So the limit as x goes to 0 for negative x squared, well, negative x squared is just an upside down parabola and it goes right through 0 and it's continuous there. So this is just 0. And the limit as x goes to 0 on the right side here, or sorry, from x squared, that's also 0. So what this says is this function right here, right, or the function itself, negative x squared, does something like this. Positive x squared, this one, does something like this. And the function that we want to look at is always in between. So, and it turns out that function actually does something like this, where it sort of bounces back and forth between those two curves. And we care about, well, what happened right around 0? Well, since the limit on the left was 0, since the limit from above is 0 and the limit from below there is 0, then we can say that ours gets squeezed into the same spot. Just like that. In fact, you could write it like this. From this line, you could just say, let's take all the limits as x goes to 0. And that's got to be, less than or equal to the limit as x goes to 0 for x squared sine 1 over x, which has to be less than or equal to the limit as x goes to 0 of x squared. And since this one's 0, and since the other one is 0, then this is stuck in between. So that's got to be 0 too.